Okay, so recording has started. Uh, so before starting, I would just like to say that if any internet connection issue happens in between, since I'm using my mobile data today, please be present. I will try to join within 10 to 15 minutes. Okay, so please wait for few minutes, and then I will join by then, by any means. Okay, so let me first share my screen. Is it visible to you guys? My screen is visible, right? Yeah.
Yes, sir.
Okay. Do let me know if it freezes or any internet connection issue happens, since I'm using my mobile data. Okay. Welcome everyone. So this is week 8's live interaction session for our course, which is on Aspen plus simulation software, basic course for the beginner. So I'm Bhavesh Moorjani. I'm currently doing my Ph.D at IIT Bombay. I have done my bachelor's from MS University Vadodara, where I was introduced to Aspen plus simulation software, and currently I'm a TA for this subject, where I help you guys to get more hands-on experience on the Aspen plus by doing various problem sets on the Aspen plus. Okay. So currently, the way Sir has designed this course is what is is that we were introduced to various models previously in the from week 1 to week 6 lecture, and then week 7 on, Sir is doing various case studies. So same method I am also following, and in today's class we will be doing 3 examples. So I have taken out 3 examples. One is a relatively big example where we will be doing process plant simulation of vinyl chloride monomer production, and then I have 2 distillation column examples. Okay, so first we will start with this question 1, where vinyl chloride monomer production process is given. So this is a process flow diagram. The process flow diagram itself is generated in Aspen plus. So as you can see, this is how the reaction goes. First, let's read out the problem statement itself, what it is, and then we will try to simulate in the Aspen plus. So we have pure ethylene stored at gas at 70 degree Fahrenheit and 1000 psi with a flow rate of 20 tons per hour, and pure chlorine stored as a liquid at a 70 degree Fahrenheit and 150 psi with a flow rate of 50 tons per hour, enters a mixture block B1 at 2 atmosphere. So chlorine and ethylene goes into the mixture. From mixture they goes into the reactor part. In the reactor, the mixture outlet F1 goes to the reactor B2, which is operated at 363 Kelvin and 1.5 atmosphere. In this stoichiometric reactor, so reactor type is also given, R stoich. The following reaction is happening. So ethylene and chlorine reacts together and forms an intermediate, which is dichloroethane. 98% conversion of ethylene happens. From there, the mixer B3 operates at 1.4 atmosphere. So if you will see here, after the conversion, reactor outlet goes to one mixer, where another recycle stream comes, and from there the mixer outlet goes to a cooler. From that it is pumped and again heated to a desired temperature, and then put it into the second reactor. So what is said that in the next, mixer B3 operates at 1.4 atmosphere, allows the which allows the mixing of recycle stream with a reactor product. The outlet is condensed fully to a liquid phase in block B4 at 298 Kelvin, and then it is pumped to an evaporator. In the evaporator, heat is supplied to again increase the pressure. So what here has been done, that we have a mixture outlet which is in vapor phase. First it is cooled down, so it is converted to the liquid phase. Then its pressure is increased by a pump. Then it is again heated to a vapor phase. Since the reaction will happen in the vapor phase, the secondary reaction will happen in the vapor phase. Okay, From there, evaporator, uh, phase change is occurring, vapor temperature is also increased till 515 Kelvin, and then it is fed to again the reactor, where the following reaction happens, that our intermediate, which is dichloroethane, is converted to vinyl chloride monomer plus hydrogen chloride. So this is the second reaction which is happening, where we get the final product. The reactor conditions are also given, that dichloroethane is converted to vinyl chloride monomer, and it takes place at spontaneously at 773 Kelvin and 25 atmosphere with 65% conversion. Now, to reduce the carbon deposition in the heat exchanger, the hot vapor stream leaving the reactor is quenched in a block B8. So quenching is like reducing the temperature. So reactor is operating at 773 Kelvin. So from there, temperature is reduced to 443 Kelvin. Quencher effluent stream is further condensed to a liquid phase, block B9 at 279 Kelvin. So here you can see, from the second reactor outlet, we have two exchangers. One is to cool down this superheated vapor, and after that, second heat exchanger will convert this vapor to a liquid phase. Okay, so it's a kind of a two-part heat exchanger. Now one might select a one heat exchanger and subcool as well as condense the vapor, but then heat exchanger area might increase, then cost of the heat exchanger might increase. So that's why it has been splitted into the two parts. Okay, so that's kind of a designing and optimization part. The outlet of that exchanger is fed to a distillation column. So we have been asked to use DSTWU unit. Okay, and from there, what is happening? DSTWU unit, first HCl is separated in the B11 block, and then B10 block. After that, the liquid product of B11 B10 block is sent to again a second distillation column, where vinyl chloride monomer is separated at the top, and rest of the stream goes to a splitter. In splitter, what is happening? So here it is written that in the B10 block, HCl is separated, which is a light key component. B11 vinyl chloride monomer is separated, which is light key component in the second column. And from the splitter, 99.99% stream is recycled back, while very few amount is just purged. Okay, so we have to simulate this complete plant using this poly SRK method. So this is the problem statement that has been given to us, right? I hope it's clear. So let's try to simulate it in the Aspen Plus. I have to first connect my VPN. Just give me a minute. Unable to check out the license. Why this is happening? Unable to check out license for Aspen Plus. No server default. The license for this product or feature could not be retrieved. Please check that you are trying to access is available in that server. There has been some licensing issues. It could be because I'm connected to my mobile data. Can you guys wait for a 5 minutes? What I will try to do is try to connect via IITB server and see if it is working. If not, then if any of you can share your screen who has an access to Aspen Plus, so we will try to solve a problem in your screen if it's possible.
No problem, sir.
Okay.
No problem, sir.
So just give me a 5 minutes. I will rejoin this link again. If it works out, then well and good. Else, I will use your Aspen Plus. Okay. Let's connect. Okay. So then the meeting. Uh, yeah, it's working, guys. It was some network issue from my end. Sorry for that. Okay. Yeah. So let's start simulating this question here. So first we will add our component. So we have ethylene, chlorine, dichloroethane, ethane, and then vinyl chloride monomer, and then hydrogen chloride. Okay. So what we will do is first let's add all these component. Just ethylene. This is biethylene. Let me do exact search. Then chlorine, vinyl chloride at HCl and then we have dichloroethane So we have added all the component: ethylene, chlorine, vinyl chloride, hydrogen chloride, and dichloroethane. Right. So these are all the components that we need. Total 5. Press next. Now we will select the method. So method has been provided to us that we have to select this poly SRK method. Now if you will see here, the various class of method filter, and if you will apply the filter for polymers, then we have this all poly methods that start with the poly. So these methods are specifically oriented towards the simulation of polymer related components. So that's why we are using poly SRK part here. Okay, so depending upon the process that we are doing and the components we have to change our methods. Run the property analysis. If any of you want to do the current simulation side by side, that is also possible. In that case, if you find an error or if you get stuck at any point, you can discuss it out at that moment only. Okay. So if you want to do simulation in background, that is also a good thing. Still processing. Okay, we have got some errors. Warning: in the physical property system, the following conventional component were not in a data bank. Warning: in physical property, MW missing for component, NRTL binary parameter for all components are 0. So we have got some warnings. So one warning is NRTL binary parameter for all component pair are 0. Your result may be inaccurate. So in that case, go to the parameters, binary parameters for NRTL parameters. If you recall in the previous classes where we don't have the binary parameters, we can use unifact method to estimate such parameters. Select that and we will run the analysis with that also. There was another error that molecular weight is not present for dichloroethane, but I think it should be. Let's run this with the estimate binary parameter using the unifact method, and let's see if we are getting same error or not.
Sir, I have a question.
Yes, go ahead.
Sir, I put the same components as you showed on the slide and also selected the same method, but I didn't receive any error. Why so?
You haven't received any error?
No, sir, I didn't receive any error.
So NRTL parameters are calculated in your result, like in your binary parameter. Can you see the NRTL parameters like this or not? Can you check?
Just a second. Parameters, binary interaction. No, it doesn't show anything there. Okay. But still, but I can show. I can share the screen. If
yeah. Just go ahead and share your screen.
See, this is the.
No, I cannot see your screen. I mean, it's shared, but I only see a white, complete white.
Oh,
can you reshare
okay,
it?
Yeah, sure, definitely. Tell me when you are able to see.
Yeah, now I can see. Yeah. So.
But it didn't show any error.
This thing ran without any error.
Yes, sir, without any error.
Okay. And the method that you have selected is this poly SRK, right?
Yes, sir. See. Okay. Also, if we want to see the components, I put the same components.
Vinyl dichloride, yeah. Okay. This I have to check why these things are happening. I'm not sure. You are also using version 14, so it's not a version issue. Let me do search about this, why Aspen Plus gives an error in one place and not in the other place. I don't have any idea about it.
Yes, sir.
Yeah. Okay. Thank you for bringing that. Yeah. Okay. So does anyone else got this error? If any of you are also doing this with me simultaneously. Okay. Anyways, results available with warning. I'm still getting a warning. Warning in the physical property system. The following conventional components were not in a data bank. Check data bank names for spellings. Okay. Components are there. It's correct. C2H4Cl2, HCl, C2H3Cl, and Cl2. Now it could be, if I dichloroethane, this is one dichloroethane. I'm not sure exactly about this error, but let me check, because previously when I did, it didn't show any error. We're not in a data bank. Check the data bank names for the spelling. Okay. Let's go to the simulation part. Now, strategy to do a simulation of any process plant. So if you know the complete flow sheet, like here we have been provided with the complete flow sheet data, is so in that case we can begin with starting with the complete flow sheet, put all the equipments, connect all the lines, and then specify the inputs. Else, uh, we can do the plant simulation by piece. So first we will simulate the mixer, then we will add the reactor, then again mixer, then heat, this cooler, pump, and so on. So both strategy are useful in cases where we have this process flow diagram already present. We can start with the complete flow sheet simulation, and in case that we are trying out various things, we are developing a process. In that cases we can do the simulation piece by piece by adding simulating one equipment first and then going ahead with the other equipments. Second strategy might be useful, particularly in case of troubleshooting, where we don't know what output to expect. In that case, we can move equipment wise and then optimize various parameters to move forward with to get an optimum or desired values. Okay, so here what I will do, we will move piecewise, like we will simulate one equipment, then another. Okay, if you want to go continuously, that also you can do. If you want to take a screenshot here, you can take it, those who are trying to follow it. So I will pause here. Then this is the reaction data. And this is the third part. 1, 2. Okay. Yeah, here I forgot to mention. Yeah, so we have to select actually 1,2-dichloroethane. This I have to change. So it has been specified. So dichloroethane, it could be like chlorine can be attached to both the carbon, or it can be attached to the individual carbon. So here we have been provided with the 1,2-dichloroethane. So just select that. I forgot about that part. So let me first quickly change the component. Find. It's taking too long. Okay, so this is 1,2-dichloroethane, C2H6. Add selected component. Let me remove this dichloroethane, delete the row. Started control. Okay, next method is poly-SRK. Let me reset it. And run it. Okay, yeah. So it could be the, now I don't see any error, so it could be the issue with the component. So I had selected the dichloroethane without providing whether it is 1,1-dichloroethane or 1,2-dichloroethane. Now I'm not getting an error with 1,2-dichloroethane. So once all the components are added, go to the simulation panel. So we have first one mixer. So I will start putting it all the components together. Feed. So feed is coming this way, that we have pure ethylene and pure chlorine coming to the mixture, and then mixture outlet is going to the reactor part. Okay. So let me put it this way. We have ethylene, chlorine. I'm writing a short form because we have a limit of 8 characters, so we cannot write complete names. Okay, anything which is convenient to you. And one out. Let's call this as a mixture. Now let's add the component. So first, chlorine. So chlorine is coming at 70 degree Fahrenheit, 150 psi at a flow rate of 50 tons per hour. 70 degree Fahrenheit, 150 psi. So and flow rate is provided in ton per hour. So let me ton is not present here, so let's change our unit to English unit, and then this is a molar fluid, sorry, mass flow rate, and then ton should be here. Okay, tons per hour. Chlorine is coming at 50 ton per hour, so 50. This we had to provide, it has changed, 150 psi A and 70 degree Fahrenheit. Add the ethylene specification. So So for ethylene, ethylene is also coming at 70 degree Fahrenheit but at 1000 psi and flow rate of 20 ton per hour. So 70 degree Fahrenheit, 1000 psi, and at a mass flow of 20 ton per hour. Okay. Once that is complete, press next and run the simulation. So that way you can see results are available with no warning. In block we can check the mixer output also. Now mixer output we haven't provided any pressure, that means it will take as a zero pressure drop in the mixture. And if you will see the stream results, so this is how it is. Okay, we see mass fraction, mass flow, both ethylene and chlorine are mixed together. Now after the mixture, mixture pressure is also given. So mixture block B1 operates at 2 atmosphere, so we have to change that. And then from mixture, outlet of F1 goes to the reactor B2 at 363 Kelvin and 1.5 atmosphere. So let's change both together. First mixture is operating at 2 atmosphere, so I'm changing that. Let's add reactor also, which is R stoic, which is added the reactor. Deconnect the line, so it will go to the reactor. From the reactor we will have an reactor outlet. Let's rename them. I will call this as R1 and this is the R1 out, reactor 1 outlet. Okay, we have two reactors, so that's why R1 and R1. Do next, add the reaction specification. So reaction operating conditions are also given. So we have R stoic reactor, conversion is given as 98%. The reactor is operating at 363 Kelvin and 1.5 atmosphere. So let's add this: 363 Kelvin of reactor temperature, 1.5 atmosphere pressure. Valid phases that we have kept as vapor and liquid. Add the reaction. So first ethylene is reacting with the chloride and forming 1,2-dichloroethene. Okay, and the stoichiometric component is 1,1,1. So 1, 1, 1. Conversion is given, that 98% conversion of ethylene happens in the first reactor. So we will add that, and the reaction data is also complete. Okay, press next and run it. Results are available with no error. So if you will see the reactor outlet, stream result, feed is coming at in the reactor is coming at 2 atmosphere. We change the mixture pressure to 2 atmosphere. Okay, reactor is operating at 363 Kelvin and 1.5 atmospheric pressure. And if we will look at the conversion, so let's look at the mass flow rate to compare it. So we had provided that 98% conversion of ethylene should happen. So we had 18,143.7 ethylene coming, and it got converted, and we have 362.897 ethylene in the output. So if you will do the ratio, it should come at around 0.98. So So let's check this. We have 362.874 divided by 18143.7, which is around 2% of the feed. So 98% conversion has happened, and then correspondingly we get the 1,2-dichloroethane. Now outlet of the first reactor, if you will see here, is cooled down, and then it is pumped, then again it is heated and put to the second reactor. Before that it is also mixed with the recycle stream, but as we are doing it piecewise, we won't be adding currently recycle stream. We will add the recycle stream at the end. If you are doing it simulation as a whole, then in that case you don't have to worry about it. Right now what we will do, we will add a mixture unit here, but we will only give it F2 stream. Only the reactor outlet we will connect with the mixture, not the recycle part, right? So what information we have, that in the next mixture B3, which operates at 1.4 atmosphere, allows the mixing of the recycle stream. The outlet stream F3 from the mixture is fully condensed to the liquid phase in the block B4, which is a cooler, at 298 Kelvin before pumping to the evaporator, and pump discharge pressure is also given as 26 atmosphere, and then evaporator working condition is also given, that evaporator heats the stream till 515 Kelvin. So let's add all these details. Since these are the small component, we can add them together and we don't have to worry about them failing. So I hope you are understanding why we are doing piecewise. In that case, we can understand better where the error is coming in our system. We have mixture also. Mixture, then cooler. From here we will add a pump. After the pump we have a evaporator. Okay, now connect all this stream. So mixture outlet is going to the cooler, cooler to pump, pump to again evaporator, and then from evaporator we will have it go to the reactor. First reactor outlet is connected to input stream. Reconnect to the destination. Okay, let's rename all this. Now we have mixture, so let's name it as mixture 2 or M2 for convenience. I will change this name also as M1. This block B3, it's a cooler block, right? So cooler 1, this is pump 1, C1 out, pump 1 out, and this is our heater, so H1 out. Okay, now add all the details for this part. So first we have a cooler. So we have been provided that cooler is operating at 1.4. Before cooler we can provide the mixture criteria. Mixture is operating at 1.4 atmosphere. Once that is added, go to the cooler. Temperature is brought down to 298 Kelvin in the cooler part. Okay, so 298 Kelvin, and the pressure. So pressure, either you can write it as 1.4 atmosphere or write it as 0. So it will consider a 0 pressure drop. Go next. We have been asked to provide a heater input. It should be pump first, but anyway. So in the heater, steam is heated to 515 Kelvin. So just a minute. We provided the mixture input, cooler input. Now first provide the pump input. So we know the discharge pressure. Discharge pressure has been provided as pump discharge is 26 atmosphere. So let's write this as 26 atmosphere. Efficiency has not been provided, so we will consider default 100% efficiency. From there it will go to the heater. So heater input 515 Kelvin temperature and pressure. So here you can write 0, so it will consider 0 pressure drop across the heat exchanger. Okay, once this is done, we can run the simulation. So all the details have been provided up to this point. Press next and run it. Now here I know we should get one error. Let's see, we are getting. So result available with the error. So what's the error here? Error: while generating the result for unit block pump 1, 1.71% vapor outlet conditions may be wrong. Okay, so net positive suction head is less than 0. So if you will see the block and go to the pump part, result of the pump. So here you can see NPSH is coming as negative, which is minus 4.358. This should not happen. I mean, NPSH can not be negative, it should be positive, right? So that means there is some issue here. What is the issue? So if you will see the stream that are coming into the pump, that C1 out is not completely liquid phase. There is some vapor fraction present inside here, right? So if you will see the molar vapor fraction, we have 0.017 mole fraction of vapor present, while the pump input should be completely liquid, right? So if you will go into the main flow stream, here let's put all the some labelings. So we will add temperature, pressure and vapor fraction data into our system. Okay, now in the vapor fraction, you see this option for detail, mole specification for detail specification. Here let's provide further decimals. So let's say we want to see the information till 0.2 decimals in the temperature and pressure part, while 0.5 decimals in the vapor fraction part. Apply it. So what we will see here is that from cooler, in our process it was mentioned that the outlet stream is then condensed fully to a liquid block at 298 Kelvin. We had provided the specification as 298 Kelvin, but still we are getting some vapor fraction. One reason for this is that here in the mix, the input of the cooler is coming from the mixture where recycle stream is also coming. So because of that, it could be that the F3 itself is at lower temperature. So at 298 Kelvin, output of cooler is at in complete liquid phase. But right now we have not added any liquid phase. So for a time being, what we can do to avoid this error, we can further reduce the temperature of the cooler. Let's say we keep it as 295 Kelvin and see if it is working or not. Run the analysis. We still have an error. So we have 1.28 vapor fraction. So still vapor fraction is there in our flow sheet. Sorry. Yeah. In our flow sheet, if you will see, still we have 0.0128 fraction. So let's try and reduce temperature further. So let me select 293 Kelvin and see. So right now I am doing hit and trial and seeing, since the vapor fraction is very less, if it is coming down or not. Still there are vapor present 1.01. So let's operate at 290 Kelvin and run it. No, it's not changing. So in such cases, what you can do, one is you can do a sensitivity analysis where we can put variable output variable as a cooler outlet temperature, and our target variable will be vapor fraction in the outlet stream, which is this C1 out. Okay, but let's say 285 and run it. This should work right now. Yeah, it's working. So with 285 Kelvin it's working. So that by right now I'm not doing this sensitivity analysis, since we know anyway we will attach a recycle stream here that will affect the complete output part. So that's why I'm not doing a sensitivity analysis. But let's say you are doing some new simulations or you are trying out new method, and in that case you encounter such error. So then in that case we don't have to do trial and error analysis all the time. You can do a sensitivity analysis where the cooler temperature is an your manipulated variable, and the calculated variable will be this vapor fraction, and see out at what point you are getting a zero vapor fraction. Okay, I hope this part is clear. So we did up to this point. Here we can also check the duty. So in this flow stream itself, we can provide the heat and work required for all the components. So for the reactor, since it's you can see the negative heat duty is given, that means energy is being released. In the cooler we have to take out this much energy, and the heater we have to provide this much energy. Okay, pump work is also given. We have simulated till the heat exchanger 1. Now after that, this output goes to the secondary reactor, where the secondary reaction happens, where our vinyl chloride monomer is formed. Okay, this is also R stoic reactor. It is being operated at 515 Kelvin. So before that, the pump outlet itself is heating it to 515 Kelvin that we have provided. It is going to the R stoic. From R stoic, the vapor outlet of the reactor 2 is cooled down into two stages. In the first reactor, superheated vapor is cooled down to a saturated vapor, and in the second part, they are condensed to a liquid phase and then fed to the distillation unit. So we will simulate this 3 reactor and 2 exchanger columns. So add a reactor R stoic. Let's say I'm adding it here. Okay. Add a exchangers, exchanger 1 and exchanger 2. Connect all these streams. So you can rotate this icons also. So let's say since now flow is moving from this to this direction, I can change just right click on the icon, and then you can see rotate icon option, flip it horizontally. Same way here, rotate icon, flip it horizontally. So it's consistent with it is consistent with our flow sheet. Okay, this is done. Connect other input streams also. Reconnect to the destination. Let's rename them. Now this is our second reactor, which is R2. Outlet of the second reactor, R2 out. This is my cooler 2. Okay. C2 out. And then third cooler, I will write it as C3 out. Okay. Now let's provide input for all this. So first we have a reactor. Reactor is operating at 515 Kelvin. Okay. Pressure value. So that will be the outlet of this heat exchanger. Where it went? Yeah. So it's in 26 atmosphere. 26 atmosphere, since we have considered there is no heat loss in between. Oh sorry, this is not a reactor outlet, this is a cooler part. Sorry, my mistake. Let's add it from flow stream itself. First we will add the R2 part, which is 515 Kelvin. Pressure is 26 atmosphere. Add the reaction part. So we will add our second reaction, where our intermediate, which is dichloroethane, is splitting into vinyl chloride and HCl. Okay. Coefficients are 1 and 1. The conversion. So here what has been mentioned, that following the pyrolysis reaction. So this is the pyrolysis reaction. For the conversion part, the dichloroethane is converted to vinyl chloride monomer, and it takes place at 773 Kelvin, sorry, my mistake, 773 Kelvin and 25 atmosphere with 65% conversion of dichloroethane. So conversion is given as 0.65 of dichloroethane. Okay. So reaction data is added. Here let me change the pressure temperature as 775. Right, and 773 and 25 atmosphere. 25 atmosphere. This data is added. Now let's move forward to cooler 2. So what has been mentioned, that to reduce the carbon decomposition in the deposition in the heat exchanger, the hot vapor is quenched to 443 Kelvin. So I will provide this as 443 Kelvin, and the pressure value, let's put it as 0, so it will consider a 0 pressure drop. Then cooler 3 input. So for cooler 3 input, our vapor product is further condensed, and it is quenched effluent is further condensed to a liquid phase at 279 Kelvin. Okay. So this outlet is at 279 Kelvin, and let's provide 0 pressure drop. All the data has been provided in this flow sheet so far. Let's run the simulation and see what we are getting. So results are available and there are no warnings. So let's see the main flow sheet here. So you can see the outlet of the reactor is in vapor phase, since we have vaporefaction as 1, where superheated vapor is cooled down and we get saturated vapor at 443 Kelvin, which is further cooled down and condensed. So we get a 0 vapor fraction, okay, at 25 atmosphere. So these are the feed data. You can see the corresponding heat duty also. Okay. In the reactor, in the R2 part, let's see the stream results also. So what is happening, we had provided the conversion based on the dichloroethane, that 65% of dichloroethane is converted to vinyl chloride. So if you will take this ratio, you will get the 35% value. Okay, that means 65% of dichloroethane has been converted, and we are getting the vinyl chloride monomer and HCl. Now, once the outlet of once the reaction has been complete, now comes the separation part. So for the separation, first vapor are cooled down, and then now series of distillation column is being used. So cooled liquid product is distilled through the DSTWU unit, where the first unit will separate HCl, second unit will separate vinyl chloride monomer, and the bottom product of the second distillation unit is split into two parts. One is purge and second is fed back into the mixture again. So let's simulate that. These are the distillation column data that has been given to us. Okay. So as has been mentioned, that first column mainly separates HCl, second VCM. Both columns are operating at 10 theoretical stages. Okay, and these are the specific conditions. Why I forgot to provide the pressure value here. First let's add the distillation column. I will give that value also. So we have two columns. Let me reorient them. Flip horizontally both. Connect the feed line. So bottom of the first column goes as a feed to the second column. Second column distillate is our output. First column distillate is our HCl. We connect the source. We connect the destination. This is HCl, so rather let me write it as D1 top. So this B4 block, sorry, let me close, there are so many windows. Let's close this. So let me write it as distill 1, okay, and this as distill 2 block. This is the D1 bottom, D2 top, D2 bottom. Okay. Now, what has been said to us, that the D2 bottom is further splitted into two parts. So we will use F split. Use this part. One will go as a recycle stream and another will as purge. So let's reconnect to this. You guys are following it. If any of you has an issue, please let me know, okay? Yeah. Reconnect to the destination. This will be our purge and this will be our recycle stream. Okay. So all these streams are complete. Now let's provide the input of each. So we have first distillation 1. Number of theoretical stage has been said as 10. Light key component in the first is HCl. So here it is mentioned that for the first block B10, HCl is the light key component, while heavy key component is vinyl chloride monomer. So and the ratio is also given. The pressure value I will mention. So pressure value for condenser and reboiler is 2022. So let me just add this column so it becomes we have condenser, then we have reboiler. So this condenser is operating at 20, reboiler at 22, 7.5 and 8. Okay. So first column is operating, condenser is at 20, reboiler is at 22 atmosphere, total condenser has been given, HCl recovery is 0.99, vinyl chloride is a heavy key component with a 0.001. Okay. These are the specification. Go next. Then DS to U unit, 10 stages. It's operating at 7.5 condenser pressure. Yeah. Hello. You have any doubt, CHM, or if not, please mute yourself. For the second column, vinyl chloride is a light key component with a recovery of 99.9%, and heavy key component is 1,2-dichloroethane, which should not go more than 0.1%. Okay. Then after comes the split fraction. So we have been said that recycle stream, 99.99% stream is recycled back. From the split, 99.99% stream is recycled back into the mixture and rest is purge. So purge is essentially to prevent the accumulation of the unreacted component, but that purge is very small. So we can provide this as, let me write this value as 0.999. Okay. So this recycle fraction we have provided. So all the data here is complete. Let's run the simulation and see what is happening right now. So results are generated without any error. So here this one. Let me do some rearrangement. Why this is happening? Okay, yeah, I think this will work. So first let's look at the distillation 1 output. So what was the purpose of distillation 1? To separate out the HCl. So if you will see the mass flow rate that is coming into the distillation 1 unit. So we have HCl coming at 15,000 kg per hour flow rate, out of which we asked for the 99.9% recovery. So almost all amount of HCl went into that. but we didn't wanted vinyl chloride to go into the first distillation top. Okay, so only 1% of that has gone to the first part. At the same time, if you will see the ethylene, so ethylene also has gone with the HCl part, since it's a more volatile. So ethylene has also gone into the distillate. Now here it has not been provided further separation of HCl and ethylene, but since ethylene is our reactant part, it's obvious to separate it from the HCl, though it is in less amount, but it can be further recycled back, right? And so this thing, that further separation might be happening in some different unit also, which has been not provided here. And the bottom part contains the chlorine, vinyl chloride, and rest of the 1,2-dichloroethane. Okay, so most of the dichloroethane is in the bottom part. From there, the second distillation column, which had the purpose of separating vinyl chloride in the top. So if you will see the D2 top, most of the vinyl chloride has came out in the distillation top of the second column, along with the so much amount of the chlorine, which also further needs an segregation, like separation part. And the bottom of the second column mainly contains the 1,2-dichloroethane. So that is an intermediate which is being utilized in the second reaction, right? So in a splitter here, if you will see, okay, so this much part we have to supply it to the second reactor. Now here it has not been mentioned that at what condition we should provide this purge stream. Even in the flow sheet also, the outlet is directly splitted and sent to the purge. If you will see, the temperature here is at 441 Kelvin. I think these are the Kelvin units, right? So 441 Kelvin, while the mixture is operating at 360 Kelvin. So then the temperature of this might increase more. But anyway, let's try and reconnect and simulate what is happening right now. So if we reconnect this recycle stream to the mixture, that is being done. Let me reposition them first. That's not happening. Okay, let's call it as split 1. Okay, this is our recycle part, and run the simulation. So before doing that, let this analyze the output of R1, what it is like, sorry, R2 reactor. So if you will see the blocks, let's look into the R2 stream summary. Right now, without the recycle, total of 68,000 kg per hour feed is coming, out of which we have 62,000 of dichloroethane, from which we are getting 25,000 of vinyl chloride monomer. Now with the recycle, let's see what is happening. So run the simulation. Results are available. Go to the result of second reactor. So now total flow rate is 1,01,000. Okay. So and then out of which 96,000 is 1,2-dichloroethane. Previously we were getting only 25,000 of vinyl chloride, but now we have 39,000. So conversion has increased because of the adding the recycle part. Okay, so that is the purpose of the recycle. Now, the one issue that we were getting near the cooler one was that we had to further lower the temperature of cooler one to 285, while in the process flow sheet itself it was mentioned that the uh, outlet sorry outlet is cooled as 298 Kelvin. So let's try with 298 whether we are still getting the vapor fraction in the pump inlet or not. So now when I have changed it, let's run it and see. So if we are running it, since you can see that we are not getting any error with the cooler one. So initially we had got an error with the cooler one, that the outlet of cooler one had it contained some vapor fraction like that, 2% or something, right? But right now it's completely in the liquid phase. This is due to the addition of the recycle stream. Okay. So this is the complete flow sheeting of flow sheet plant, like process plant simulation of vinyl chloride monomer manufacturing unit. Now in this simulation, we haven't looked much on the optimization part. This is just kind of a, if you have given any process plant, how to simulate into the Aspen Plus. Now in this you can further do optimization using various process analysis tools. So we had seen in the previous lecture, right, that in the model analysis tool you have sensitivity, you have optimization, constraint and data fitting. So we can add, we can do sensitivity analysis. Let's say in the reactor 1 outlet we want to, if you will see R1 out, where is R1 out? Yeah. So stream summary of R1 out. Mole fraction. So here only this is straightforward, that ethylene is being converted to our intermediate, which is dichloroethane. So here nothing much we can do. But let's say for the R2 part, in the R2 stream we have dichloroethane being converted to the vinyl chloride monomer, and then we want to increase the conversion of vinyl chloride monomer. Then you can do this sensitivity analysis and see how much dichloroethylene you should include to increase the conversion. Or suppose the recycle stream. So here it was given that 99% is being recycled back to the mixture, and then it goes to the reactor. But let's say if it wasn't mentioned, and then we had to decide how much feed to recycle back. In that case, this split fraction can become our manipulated variable, and our target variable might become the outlet of the R2 unit, where molar flow rate or mass flow rate of vinyl chloride monomer is being checked with this recycle part. So such sort of an analysis can be done, but right now the objective was to translate complete process plant unit into Aspen Plus simulation. Okay, so that has been done right now. So this is the example 1 for today's class. Do any of you have an error, or any of you were trying to simulate this in background? If you got it, or if you found any issue with that, you can say it out, or we can move ahead. No one? So were you guys trying, or you will try it out later? I mean, he, Bhavna or Pratiksha? At least you can answer yes, no. Guys, this is an interaction session, so you have to speak it up, right? Will you do it later? Yes or no?
Yes, sir.
Okay. Do try it out, and if you are facing any issue, let me know. So sometimes, I get a message from students that they are facing issue, or even in the last time, in the previous lecture, one student came with some query. I asked him to stay at the end, because I have to finish one module and then I can look into the other errors. I cannot directly solve your issue without looking into it. So in that case, please reach out. Uh, Apart from this live interaction session, you can mail it also. I will try to respond to you within a few days. Okay, but try it out. So with the more practice, you will get better into this. Okay. So if this is done, let me first save it and then we can move forward with the another example. Okay. Okay. Meanwhile, it's loading. Let's look at the second case study. So this is a relatively simple example. So if any of you want to do it in your Aspen Plus by sharing your screen, we can do that also. So this example is a distillation part that hydrocarbon stream with a component wise flow rate has been provided in this table enters into the isentropic compressor at 120 degree Fahrenheit and 1 atmosphere. Compressor discharge the vapor stream at 3 atmosphere. The complete process flow sheet for flashing and stripping operation is given in this figure, which is figure 4.58. So we have feed coming, hydrocarbon mixture coming into the compressor, which is fed to the first flash unit. Liquid product of the flash unit is then sent to the stripper part. Okay. What other information we have? The flash drum is running at 125 degrees Fahrenheit and 2.8 atmosphere, while stripper has a total 6 stage including condenser reboiler. Bottom to feed ratio has been provided, and we have to use this strip 2 unit in the Aspen Plus. Okay, the feed stream to stripper is introduced above the top stage and the pressure throughout the column is 2 atmosphere. We have been asked to simulate this plant using UniQuack method to compute the product composition, flow rates, and then do the sensitivity analysis to understand the effect of change in pressure and temperature of the flash drum on the vapor flow. Okay, so this is a relatively simple problem. Let the new simulation start and then we can go. So do any of you have an access to Aspen Plus right now and want to share your screen and try this example, since it's a simple example, or should I do with my PC only? Okay, no response, so I will assume I have to do it. Okay, so let's wait. Once it is loaded, we can move forward. Yeah, it's ready. Just a minute. This is working. Record is working. So we have a hydrocarbon feed. So all the C1, C2, C3, C4, C5 and C6. So C1 to C6 component has been provided to us. Let's add all the component. So we have first methane. Then we have ethane, propane, butane, pentane. So by default it is adding N-butane and N-pentane, but let's say if you have a isopentane or isobutane, then you have to manually search it. Okay, then last we have hexane. property method that has been provided to us. So we have to use unique vac method to simulate the plant. All the components are added. Go to the property selection part. We will be selecting unique vac method. So unique vac, go next. Let's select this, estimate missing parameter if there are any using univac method, and run the simulation. Wait for a few minutes. Flash and stripper. This is the flow information. Result available with warning. Warning in physical property system. The following conventional components were not in the data bank. It shouldn't be there. These are the conventional component. NIST. Organic, inorganic. I'm not sure why this error I'm getting of the following conventional component are not present in the data bank while I have selected the default data bank. So let me know if you guys also see the same issue, okay? And then it will help me to find out whether I have to debug it or it's a general error. Okay. Anyway, let's go to the simulation part now. So what is the process flow sheet? It is this way, that feed coming to the compressor is fed to the flash and the stripper. So first we will select a pressure changer. We have a compressor. After that we have a separator, flash 2, and then now here one thing, in the column we have been asked to use strip 2 part. If you will see the description, it has been asked that we have to use the stripper strip 2. And if you will see the default option that you have in the column section, you won't find any strip 2 here. You have DSTW, distill, red flag, extract, and these are the multi-component fractionator. In the separator also you don't have it, but in the further option like in the red flag, if you will click this option, you get other versions of the red flag also. Okay, so you have fractionator 1, frac 2, this is your strip 1, strip 2. So essentially they are working on the same phenomena, like all the governing equation in this model will be same, but there will be slight tweak in the sum part. So let's say right now I am selecting strip 2. So the difference in the red frac and the strip 2 is that if you will see the top part, the condenser is not provided. So it's just operating as a stripper. As in we are more concerned related to the reboiler duty part rather than the condenser part. Okay, so that way. So in the calculation of the strip unit compared to the red flag, we won't be concerned about the condenser parameter, so that will be neglected. So that is the difference between the other alternative option under any component. So either it could be the icon change if you want to do it, or it would be tweaking the some parameter. So like this rectification unit, so if you want to, if you are more focused on the rectification part, like top part of the distillation column, you can use this unit. If you are interested in the bottom part, you can use this stripping section. This rectification is also called enrichment part, right? Then you have absorber and other units also. Okay, so governing equations are at the end same, but there is slight modification in one or two calculation parameters or equations. Okay, now connect all the components. Bottom of the flash unit goes to the stripper part. We have vapor. Let me provide the nomenclature same as the flow sheet. So we have H, compressor, F, V1, V2, liquid 1, liquid 2, flash and stripper. So this is a hydrocarbon mixture, goes to the compressor. Okay, then we get a feed F. Outlet of the flash, top outlet is V1. This is a flash unit. We have a liquid outlet as L1. Then we have a stripper. Okay, so stripping section V2, and this is an L2 part. Right. Now the process flow sheet is ready. Let's add the input part. So what has been provided to us, that feed is coming at 120. Feed enters the isentropic compressor at 120 degree Fahrenheit and 1 atmosphere with the following flow rates. So feed is at 120 degree Fahrenheit, 1 atmosphere, and molar flow rates are given in pound mole per hour. Okay, so methane is 15, C2 is 95, 15, 95, 150, 25, 10 and 100, 150, 25, 10 and 100. Okay, so let's verify. 15, 95, 150, 25, 10 and 100. 15, 95, 150, 25, 10 and 100. These are, flow rate is in kilomole per hour. My mistake. It's in kilomole per hour. So yeah, here flow rate is in kilomole per hour. 120 degree Fahrenheit. Let me just confirm this once again. Yeah, it's correct. It's in kilomole per hour. Okay. Then go next. We will have a compressor. So compressor has been said as it's an isentropic compressor, and the discharge pressure is given that compressor will discharge the vapor at 3 atmosphere. Compressor discharge vapor stream at 3 atmosphere. Sorry, wording is incorrect. And 3 atmosphere discharge pressure. Efficiency has been not provided, so we will take default efficiency as 100%. Then the flash input. In the flash drum is operating at 125 degree Fahrenheit and 2.8 atmosphere. 125 degree Fahrenheit and 2.8 atmosphere. Now the stripper part. So as I was saying, that stripper part is kind of the same as the right flag, only some modification will be there. So what information we have for the stripper? That stripper is operating at with a total of 6 stages, which includes condenser and reboiler. Bottom to feed ratio is given as 0.8. The feed stream to the stripper is introduced above the top stage, and the pressure throughout the column is 2 atmosphere. Okay. So total number of stages will be 6. Now in the condenser part. So if you will see, although the problem statement says that stripper includes like total stages including the condenser and the reboiler, but for the calculation of the stripper we are not more concerned about the condenser which has been attached to the stripper unit. So that's why in the condenser option we will select it as none. Okay, no condenser. So reflux is provided by so you can see the description also. For the no condenser, reflux is provided by external feed, so we don't have to worry about the reflux ratio and related specification. So if I select the none, and we know the bottom to feed ratio as 0.8. Once you enter this information, you can see the reflux part went away. So we need only one information. Since why we don't need a reflux part? Because we have anyway said that we are not concerned about the condenser. So this particular calculation is not being happening right now. That's why this information we don't have to provide. So that's why that once we provided bottom to feed ratio, other information went away. In this stream, it has been said that feed is coming at stage 1 at the top, right? The feed stream in this stripper is introduced above the top stage. I mean that means it is entering at the top part, and the pressure throughout the column is 2 atmosphere. So pressure, here stage 1 pressure, which is 2 atmosphere, and pressure drop for the rest of the column. So let's provide it at 0, since it is mentioned that complete column is operating at 2 atmosphere. All the informations are complete. Run the simulation. So results are generated and there are no errors. So let's see each result here. Okay. See, condenser duty is provided 0 since we selected the none. Flash duty is provided. The boiler duty is provided. It's negative, that means energy is being released. compressor load is provided. Now let's look at the separation part. So what has been asked in the question is that use this unique method to compute the product composition and the flow rate, and then do the sensitivity analysis to understand the effect of change in pressure and temperature of flash drum on the vapor flow. So let's look at the flash drum result. If you will see stream result of the flash drum feed, which is a mixture of hydrocarbon, is being splitted into the liquid and vapor part. Now since feed contains C1 to C6 component, like from ethane to hexane, what should be the light component which will be present in the vapor? Top ones, right? Methane, ethane, propane, that will be the relatively lighter compared to the bottom three, butane, pentane and hexane. Okay, so if you will see, methane has almost gone to the vapor. Ethane from 2856 has completely gone to the 2835, so almost complete ethane has went to the vapor fraction. Same goes for the propane also and butane also. While for pentane and hexane, pentane amount is still relatively high, from 721 kg per hour. Only 148 kg per hour pentane is going into the liquid phase, while rest is going to the vapor phase. Same is for the hexane. That hexane amount from 8600 to 5000 is going into the vapor phase. So if you will take this ratio, 5009 divided by 8617, so around 58% of hexane has also gone into the vapor phase, right? Now let's look at the stripper part. The stream result for the stripper should be here. Yeah. So in the stripper, outlet of the flash drum is coming, and which is separated into two parts. What has been said that, see, not mass fraction, I am interested in the mass flow. Okay, so the purpose of the stripper should be that whatever rest of the light component has been present into the liquid outlet of the flash one, like flash drum, they should go away into the stripper part, vapor product of the stripper. So that is happening. Like methane is going completely, propane whatever has remained is going completely. Same goes for the butane, while the pentane and hexane part, they should remain within the liquid product. Okay, there is some amount of pentane and hexane also going into the vapor, but that relatively is less. Like out of 3600, only 285 kg per hour hexane is going on into the vapor phase. So 285 divided by 3607, which is around 8%. Okay, but what has happened in the flash drum, around 58% of hexane went into the vapor phase, while in the stripper column only 8% of the hexane went into the vapor phase. So let's say we want to modify our process parameter. We want that in the V1 stream itself, lighter component up to C4 should go into the vapor part, while the heavy component, which are the pentane and hexane, most of them should remain in the L1, liquid one. Okay, and out of that, the further rest of these light component which are present into the L1 liquid stream, they should get separated into the V2, and pentane and hexane should go into the L2 part. So we want to optimize our parameters of the process. So we don't know at what condition we should operate the flash. Okay, so right now flash is operating at 125 degree centigrade and 2.8 atmosphere. So let's say I want to change the condition such that I am getting more hexane in the liquid product and less amount of the hexane in the vapor product. What should I do? What could be the possible scenarios that you guys can suggest? You have any idea? Any suggestions? Should I increase the pressure of the flash? Should I decrease it? Should I change the temperature? What should I do? Come on, think about it. So with increase in the pressure, so C6 is a very heavy component, right? So if you will remember, if you have studied the refining part, or even in the normal distillation mass transfer operation also, like for the heavy component which are difficult to boil at the atmospheric condition, what we do, we reduce the pressure to increase the relative volatility for a better separation, right? So right now we are operating at 2.8 atmosphere, where we still get this light component into the vapor product. So if I increase the pressure, then chances are that this hexane might not go into the vapor part. Okay, so one thing is to increase the pressure, another is to play with the temperature, but that will also affect our other component composition also. So first let's do some sensitivity analysis and see with the pressure of the flash how hexane products changes. Okay, so you will see this model analysis tool. In that, go to sensitivity, add new sensitivity S1. So here you have to provide manipulated variables. Okay, so add the new variable. We want to change the pressure of flash drum. Okay, so I'm using block variable. Flash is my block and variable is pressure. So search for that specified pressure for the flash. Okay, so we have selected this variable. Right now we are operating at 2.8 atmosphere, but let's say I'm starting from 2 or let's say 1. Feed is coming at 1 atmosphere, right? So no, starting from 2 and we go till approx around 10. Okay, unit I want to select it as atmosphere, since in the feed itself we have provided it in atmosphere. Increment, I want to see with the increment of 0.5 atmosphere how many point I will get. Let's say we want 50 points in between. So this is the one manipulated variable. So we will vary the pressure of flash drum and see how the hexane flow rate is changing. So for that we will add our variable hex flow. It's a stream property, so select that, and let's say I want to see the mass flow rate. So mass flow stream, either we can look at the vapor outlet or the liquid outlet. So let's say I'm looking at the vapor outlet. We want to minimize hexane in the vapor, so select the component as hexane. So kg per hour of hexane in the vapor flow rate will be calculated and tabulate the result. So use field variable option, okay, and run the simulation. It will take some time since we have selected 60 number of data points. If you want, you can reduce the interval also, the delta interval for the pressure, then in that case you will have less point, but it will run faster. So results are available. Let's see the results. So with varying pressure, we can see the hexane flow rate in the vapor phase. Like with the increase in the pressure, hexane flow rate is going down. Yeah, you can plot that also. If you will select here the top part and do custom, x-axis will be the pressure value, which is our variable and manipulated variable, and the calculated variable is hexane flow rate. So you can see with the increase in the pressure, hexane flow rate in the vapor phase is going down. So increasing pressure will help, right? But here there is one catch. So we don't only have a hexane in the vapor, we also have methane, ethane, propane, butane also. So let's say my prime focus in the V1 is that majority amount of C1 to C4 should be separated. Now C1, C2, C3 are the light component, so they will be easily separated, that I know. But I am not sure about the C4 part, since it's a heavy component. Increasing pressure will also affect the flow rate of C4. So let's see if we add one more variable to check what will happen with the flow rate of butane when I increase the pressure. So we will add butane flow as a second variable. Mass flow, V1 stream, and select butane. Okay, run the analysis and you can see results are available with no warning. So in the result part, oh sorry, my mistake, we have to tabulate this also. Fill with new variables, both hexane and butane flow rate, and then run the simulation. So results are available. Now we have both butane and hexane flow rate. So let's plot it out and see what is happening. Our x-axis is pressure, y-axis will be hexane and butane flow rate, and see. Let me merge both the y-axis. So what is happening, although increasing pressure is helping me to bring down the hexane amount in the vapor phase, but it is also affecting the butane recovery. Okay, butane amount is also going down. So let's say, show the tracker part. At around 7 atmosphere, we are getting 1100 kg per hour flow rate of hexane in the vapor phase, and same for, if you will see, at 7 atmosphere we are getting 846 kg per hour. So right now we are somewhere here, where from 1300 to 864, that is also quite a good amount of reduction in the butane flow rate that we don't want. Okay, anyway butane amount is less in the system, so this percentage reduction, if you will see the flash stream summary. In the mass flow, butane is anyway coming into 1400. Out of that, if only 800 will go, that means significant amount will be left into the L1 part. Okay, so increasing only pressure is not a good option. We can also look at what will happen when I change the pressure as well as temperature, since the flash variables that we provide in the flash drum are not just pressure, it is also temperature. So for that, let's further modify our input part. Let's add new manipulated variable, the second variable, that is also again a block variable, flash block, and I want to look for the temperature of the flash block. So specify temperature, select that. I'm selecting degree Fahrenheit unit. So right now we have provided flash operating at 125 degree Fahrenheit. Okay, so let's start with 125, let's say 100, till up to 300 degree Fahrenheit we want to go, and again let's say number of points we want 50. Okay, in between. Now if you will see, the way Aspen Plus will do sensitivity analysis is that for both hexane and butane at each temperature, so now we have two variables. For pressure also we are varying pressure from 2 to 10 at with the interval of like with 50 points, and for same goes for temperature, we are varying from 100 to 300 with 50 interval points. So 50 into 50, you have 2500 data points, like all the combinations of pressure and temperature. So Aspen Plus will do the calculation for all the combination and will give you the results. So let's run it and wait for the result. What happened? It's showing results are available. So here you can see there are two variables. So from the top itself, pressure value is starting from 2.0265 and it's continuously that. So it is doing, it's first picking one pressure and then varying the second variable, which is temperature. So at one pressure, it is looking at all the temperatures till 300 degree Fahrenheit. Once that search is done, so it is shown in the centigrade, but it will go till Fahrenheit, right? 300 Fahrenheit. Then it will vary the temperature pressure value again, and then again look for all the possible temperatures at that pressure value. So this way the iterative analysis will be done. Like for one pressure, all the look for the all the temperature. Same way for the one temperature, look for the all the pressures. In that case, how to analyze this result? How to see how butane and hexane flow is changing with the time? So this 2D plot might not help, since we have this is kind of a 3D plot. So for that you can use this 3D surf plot. So let's create that. Variable 1 is the pressure, variable 2 is temperature, and dependent variable is hexane flow rate. Do okay. Plot it out. So you can see now you have this 3D plot being generated, where hexane flow rate is a variable, like calculated variable, and manipulated variable are pressure and temperature. So from here you can find one point where you can rotate it out. So you can see after there is tracker also present. So if I want a minimum hexane flow rate in the vapor phase, what should be my operating condition? My pressure value should be 9.8 bar, 9.8 atmosphere, and temperature should be 42.92 degree centigrade. From here also you can see these are the points. If I reach the temperature value of 55 degree centigrade and then I vary the pressure, or sorry, at this pressure if I vary the temperature regardless of any value, I get the maximum amount. All the hexane will come into the vapor phase. So this is kind of your boundary, and you want to work somewhere in this optimum region. Now our second variable, which is the butane flow rate, also we want to see that also how it changes. So select hexane and then butane and run it. So we have one plot for the hexane, one for the butane. From the hexane, what we found that somewhere around 8 atmosphere and 41 degrees centigrade you will get a minimum amount of hexane. So what happens to corresponding butane there? So somewhere around 8 atmosphere and 42 degrees centigrade. 8 and 42, this way. So you can see this is your 570, around 570 kg per hour butane amount, okay, and this is the maximum amount that it can go. So this way you can decide what condition to be select. Now you have both temperature pressure diagram present and how your variables are changing with time. You can see for hexane you have some gradient in this plot, while for butane you can see that it's decreasing rapidly. So you can select some optimum point which satisfies your desired desired specification of your process, like desired condition of your process, of how much hexane to be included in the vapor phase, and corresponding to that how much butane will be lost into the liquid phase from the flash drum. Again you have second from there you also have a secondary sweeper. So let's say you decide some condition where no amount of hexane is going here, it will come with the cost of butane going inside the liquid phase, but then you can optimize your stripper parameter to recover that butane into the vapor phase. So in a way it's kind of a optimization process that you have to select. That will also further include the cost of operating condition of both the flash and stripper. So this way you can do a multiple sensitivity analysis by taking in account of many variables from your process, okay. So this is the end of the second question. Now since we are out of time, the third question, which was of azeotropic distillation, that we will do in the next class. So I will stop it here. So if you guys have any doubt, you can we can discuss it out, else I will stop the recording. So any of you have any doubt? You got the idea, overall idea what we are doing right now? Yes, no?
Yes.
Yeah. So do try it out. I will upload this documents on the Google Drive. Link is already shared with you. No sir. Mihir, what issue you like, what part you didn't understand, Mihir? Can you say it out? Then it will be easy for me to understand. Jeevan and Pratiksha, you guys got the idea, right? Yeah. So do try it out. Once you will do more examples, more simulation examples, and more trial and error kind of a thing, and then you will get more familiar with the software itself, how to use it, under which condition, what options you can select out, okay. So it's kind of a doing more practice on the simulation, then you will be able to assess better real world examples, okay.
Hello, sir.
Yes.
Sir, I also have an issue about Aspen software.
Yeah, go ahead. What issue you have?
Sir, it's license checkout.
License checkout. Okay, then we can look it out. So for the recording part, I will close it out. Then you can share your screen and we can discuss that issue. Okay. So I will stop the recording.
Okay, sir.